Hi, welcome to your MECH 200 Statics online classes. In this video, we'll finish the content of Chapter 5 of the textbook about equilibrium of a rigid body, in which we are going to extend the solution procedure of the equations of equilibrium to 3D problems. I hope you enjoyed this video. As stated in the second video of this chapter, the conditions for equilibrium of a rigid body requires that both the resultant force and the resultant couple moment acting on the body be equal to zero. In a general form, these two conditions can be expressed mathematically in vector form through these two equations, in which for the 2D problems will be extended to these three scalar equations that we use it to calculate the values of up to three unknown reaction forces at the supports that will ensure the equilibrium of a body. For three-dimensional problems, the vector equation above will be extended to three scalar equations for the equilibrium of forces acting on the body in the three directions, plus three other scalar equations for the equilibrium of the couple moments acting in each direction of the body. Totalizing now 6 equations to be used to determine 6 unknown reaction forces acting at the support of the body. However, in order to fully ensure equilibrium of a rigid body, it's not only necessary to satisfy the equations of equilibrium, but the body must also be properly held or constrained by its supports. In this case, we can have either over-constrained bodies, which have more supports than the necessary for equilibrium, and on the other hand, we can also have under-constrained bodies, which don't have enough supports, or the supports may be arranged in a particular way that could cause the body to move. And that's all we want to avoid in statics. Let's start with the over-constrained cases, in which a body has redundant supports, that is, more supports than are necessary to hold it in equilibrium. In this case, the body becomes statically indeterminate, and this means that there will be more unknown loadings on the body than equations of equilibrium available for their solution. Let's take the 2D beam here as an example, in which we have three supports at A, B, and C. If we draw the free body diagram for this beam, we know that three supports will generate 5 unknown reactions: MA, AX, AY, BY, and CY. However, only 3 equilibrium equations can be written for this beam. The same kind of situation happens in the 3D representation of a pipeline assembly shown here, in which the single bearing support at A and the fixed support at B will generate 2 reactions at A plus 6 reactions at B. As we could see in the previous slide, we have only 6 equations to solve this 3D equilibrium problem, and then the problem is statically indeterminate. If we look carefully at those 2 examples, in fact, only the fixed support at A for the beam and the fixed support at B for the pipeline would be necessary to ensure the full equilibrium of those structures, if we're not considering any deformation in the body. And all the other supports are redundant. We also have situations in which supports may be applied in an improper way, every time that it cannot guarantee that the body will maintain the equilibrium when subjected to certain external loadings. As an example, let's take these 2 beams here with the pin and the roller supports shown at A and B, subjected to an external loading P. It's clear from the free body diagram for this structure that the vertical component of P will create a moment about point A that both connections cannot support, and the result is that the beam will rotate about this point and the structure will fail. Another example can be shown in this figure here, in which the beam is supported by two rollers at A and B, and the load P is applied at the top of the beam. Here, both rollers are not prepared to support the horizontal component of the applied load, and the consequence of that will be the beam sliding over the X direction. Another example is the 3D L-shaped bar supported by three cable connections and subjected to the perpendicular force shown here. Since the cables can only support forces oriented through their directions, like the weight of the bar for example, it's obvious that the applied force will make the bar move along the direction of the applied force. In all these cases, the problem is not statically indeterminate, because there's nothing wrong with the number of unknowns reactions and the number of equations available. Here, the issue is that the structures are improperly constrained, and this situation should be avoided in structural engineering practices, since they will cause an unstable condition. Let's summarize now the procedure of analysis for rigid bodies equilibrium problems in 3 dimensions. First, we should start with the free body diagram by drawing an outline shape of the body, showing all forces and coupled moments acting on the body, establishing the origin of the X, Y, and Z axis at a convenient point and orienting the axis so that they are parallel to as many of the external forces and moments as possible, labeling all loads and specifying their directions, and indicating the dimensions of the body necessary for calculating the moments of forces. Then we are ready to solve the equations of equilibrium, in which we have to apply the 6 scalar equations if the applied forces and moments are well aligned with the axis of the coordinate system and seem easy to determine. Otherwise, we should use the vector equations, preferably in the Cartesian form. Also, there is no need that the coordinate axis chosen for the summation of the forces coincide with the set of axes chosen for the summation of the moments. In fact, an axis in any arbitrary direction can be chosen for summing forces and moments. And finally, we have to choose the direction of an axis for moment summation, such that it intersects the lines of action of as many unknown forces as possible. This will make the moments caused by these forces equal to 0, which will facilitate a lot the solution of the moment equilibrium equations. Now, let's go through the solution of one example using the scalar analysis. In example 5.15, we have this homogeneous plate shown here, which has a mass of 100 kilograms and is subjected to a force and couple moment along its edges. If the plate is supported in the horizontal plane by a roller at A, a ball and socket joint at B, and a cord at C, we have to determine the components of the reaction at these supports. To solve this problem, we start by drawing the free body diagram, in which we isolate the plate from its connections, draw the outline shape, and place the 3 coordinate axes. The location of the coordinate axis was strategically chosen at point B because we know that the ball and socket joint has the largest number of unknown reaction forces, and the moment created by these forces about B will be 0. Making the solution of the moment equilibrium equations much easier. Next, we have to indicate in the figure the external applied loads, which from the information given in the problem statement are 3. The downwards 300 newtons force applied at one of the edges of the plate, the 200 newtons meter coupled moment applied at another edge of the plate, and the weight of the plate of 981 newtons applied at the center of mass of the plate, located at its center. Now, we have to include in the free body diagram the unknown reactions at the supports, which we can readily identify as the vertical reaction force in the roller at A, the three reaction forces in the X, Y, and Z directions at the ball and socket support at B, and the vertical tension in the core TC. And finally, we have to show all dimensions in the free body diagram. At this stage, we know that we have 5 unknowns, which are the 5 reaction forces shown in the free body diagram, and we need 5 equations to calculate them. In order to calculate them, let's use the scalar analysis starting with the equilibrium equation for the forces acting in the x direction. Since Bx is the only force shown in the free body diagram acting in this direction, and there is no other force to counterbalance it, then the solution for this reaction force is 0. Next, by taking the equilibrium equation for the forces acting in the y direction, the same thing happens with By, and the solution for this reaction force will also be 0. Now, by taking the equilibrium equation for the forces acting in the z direction, we have that according to the free body diagram, AZ, BZ, and the tension in the cord TC are assumed to act towards the positive z direction, while the 300 newtons applied load and the weight of the plate are acting towards the negative z direction. In this equation, we have 3 unknowns, which means that we need to get 2 additional equations to solve the problem. One of the equations comes from the summation of the moments about the x-axis being equal to 0, in which by following the right-hand rule, we have that the weight of the plate with the 1 meter moment arm generates a positive moment. The applied 300 newtons force with the 2 meters moment arm also generates a positive moment. And the reaction force AZ and the 2 meters moment arm generates a negative moment about the x-axis. We can solve this equation for AZ directly, and we get the result of 790 newtons. The last equation we need can be taken from the summation of the moments about the y-axis being equal to 0, in which by following the right-hand rule for this axis, we have that the weight of the plate with the 1.5 meter moment arm generates a negative moment. The applied 300 newtons force with the 1.5 meters moment arm also generates a negative moment. We also have the negative applied moment of 200 newtons meter, and the tension in the core TC with the 3 meters moment arm generates a positive moment about the y-axis. We can solve this equation for the tension in the cord, and we get the result of 707 newtons. Finally, we take those 2 results and plug into equation 1 and get the value for the last unknown BZ, which is minus 217 newtons. The negative sign here indicates that BZ acts downwards. Now, try to study example 5.16 of the textbook. Before you do that, carefully review the procedure of analysis provided in slide number 5 of this presentation. And with that, we have finished chapter 5. Thanks for watching, and I'll see you in the next video.